Excellent. Hey, welcome everyone. Welcome to this next series in our webinars. We're switching to Zoom, so apologies for we're trying to find our way a little bit here, but it's pretty open and easy software. We're very happy that you're all here, and we'll be here with Tom Schoen, who's responsible for the team in the US. Renier Stortelder, who is our in-house optometrist, and Dr. Barry Leonard, one of our users in California. And we're so happy that he's joining us today as well to share a little bit of his experience. The theme of today is deep dive into first lens fit. And so we're excited. Keep questions coming, preferably via the chat, and we'll try to pick them up and answer them. Take this and make this into a nice interactive session. So without much further ado, let's get the show on the road. And Tom, are you ready to take it?
I am indeed. Excellent. Yeah. Brooke and Karen are still trying to get in, but anyway, if she can't get in, we'll send them.
I will get busy with that.
Okay. Yeah. All right. So this is the ESP First Lens Fit Deep Dive webinar, and it was put together for those who watched the 4.4 webinar and wanted to dig a little deeper. But anybody obviously can be here, which I think folks are. So on the call today, up on stage, so to speak, is Dr. Barry Leonard, Renier Stortelder, and Arnie and I. And so let's get rolling. So the agenda looks sort of like this, but this is a relatively small group, so anybody can jump in anytime. You can unmute yourself and ask a question. If there's background noise, that just asks you to put yourself back on mute, but it doesn't seem like there's any problem right now. So I'm going to go through scleral topography. Then I'm going to kick it over to Renier and Barry to talk about the first lens fit process and how that's going to really improve your efficiency when fitting sclerals. And then I'm going to be back up. We're going to answer questions. Then I'll wrap it up. And then I'll talk quickly about next steps. Whoever's got the baby in the background, hi baby, but maybe.
Yeah, I'll mute.
Okay, Brooke's in there. All right.
Yeah.
Okay, so quick overview on scleral topography. You guys all know this stuff because you're here. And what I observe and what I've seen in this segment for a long time now, I first met Arnie and Eaglet back in what, 13, when Charlie and I owned Alden Optical. He came to us to try and develop algorithms for the Zen lens. So I kind of understood what was going on way back then. And frankly, the more we learn about the sclera, the more complexity is revealed, and we're still learning. As an industry, we're all still learning. You guys are learning. I'm just trying to pay attention to what you're learning. And I think this is going to be the future, especially lens fitting, scleral topography, and that things are really going to change over the next few years. And scleral topography can dramatically decrease your chair time while improving your fits. So that's what I see as the reality here. Sclerals in general is one of the fastest growing contact lens segments, at least in the US and North America it is. I don't know the status right now in Europe. And the more you learn about the sclera, this is the vicious cycle, the so-called vicious cycle. The more you learn about the sclera, the more designs advance, scleral designs advance in particular, and the more scleral topography is needed. And that thing goes around and around and around. And again, I think diagnostic lenses are going to be a thing of the past in the next couple of years. So with that, I will hand it over to Renier, and he's going to dig into the deep dive.
Thank you, Tom. I will start sharing my screen. Give me a moment. All right, so I hope that everyone can see my screen now. Can you confirm, Tom, that you're seeing my screen?
We do.
We do.
All right.
Great background.
Sorry? Oh, thank you, thank you. Yeah, we'll move away for a moment. All right, so the topic for today is first lens fit algorithms. So I will start explaining what is it. I will be talking about the options we have, and I will be showing that it's easy and everything is just shown on one screen. Quite specific options, and after that I hand it over to Barry, who is going to present a Zenlens case. And I mentioned that already. So first I just play a little recording of my screen showing what the first lens fit algorithm is. You just select the supplier, you select the lens type, a lens diameter, and you hit calculate. It takes about 20 seconds and it is coming up with a lens prediction. So in the past, I used to go very fast here because it's just click, hit and run. So that seemed to be, yeah, not much to tell about it because it's just you click a button, you select the lens you want to have, you click a button, and there it is. But actually, I wait a moment.
Whoever has the baby running around in the background, while we love babies, please put yourself on mute. Thank you.
Because actually, there is quite a lot to explain about what is happening in the background. First of all, first lens fit is what we call our automated fitting nomograms. And how does it work? You take a measurement, you hit the calculate button, and all the cloud data, so all the raw data we have is pushed to the cloud, processed, and it returns the lens prediction. If we look at what is happening in the cloud, we have our raw data, which is up to 500,000 data points. First of all, we check the quality of the scan. If it's really missing too much data, so the coverage of the scan is too low, it will return an error. If the quality is good enough, it starts to move to step 3, removing unreliable data. I've called it unreliable. It's probably not the correct word, but what you see the 3D cloud moving there, and first of all, you notice the red dot on the right side, which is a pinguecula. The algorithm tries to remove this as much as possible. So it tries to detect a pinguecula and remove it. Beside of that, it also is trying to detect if the measurement was or is containing the tear meniscus, because the tear meniscus may give false sagittal height data. So also this is cut off. After that, the data is rotated and extrapolated. That means that based on what lens you're going to use, so the lens diameter, the data is rotated in such position that it's giving the best results. And if there is, if it's necessary, it's extrapolating the data as well. So for example, when you're going to fit very large lenses like a 90mm Boston side lens, it's extrapolating the data to get it fit. After that, we trim the data because we have to go down from 500,000 data points to only the 4 or 5 numbers you need to order the lens. So for example, what you see on the right side here, you need to know the sagittal height, the base curve, and 2 APS values. So that's the process, what's happening in this 20 seconds that it's taking after you hit the calculate button, pushed it to the cloud, and returning it to you. feel free to ask any questions about how this works, but I will move on to the second topic about what options that we have in our algorithms. First of all, we predict the sagittal height of the lens, and we include the settling as well as apical clearance, and we follow the lab recommendations as much as possible. So on average, you can say 100 microns of settling plus 300 microns of apical clearance. Landing zone, we have the option for spheric lenses, toric lenses, and also quad-specific lenses. The algorithm is aiming for a sealed or a near sealed fit. It's also what the lab is recommending. I would say on average, the steep meridian is lifted by about 100 microns, but it's really lab dependent. So we're listening to what the lab is recommending, and this is how much looser we design the steep meridian. The algorithm is also predicting what will be the rotation. So it's showing what is the rotation of the flat meridian of the lens. And beside of that, it can also predict the base curve. So it's checking what is the best uniform alignment of the optical zone. It's not possible for every lens design, but the possibility is there. Our algorithm can do it. On the right side, you see two options. The AccuLens Maxim lens is showing only the sagittal height data and the base curve. With the Maxim lens, it works this way, that you only have the possibility, or the algorithm itself is only giving you one of the diagnostic lenses. And the way AccuLens is working is you put the diagnostic lens on eye, you do your over refraction, and after that you send in the Eaglet measurement plus what trial lens did you use and the over refraction, and they will do the designing process in their CAD system, which is focal points. The other option is that all the calculations are done in the cloud on our side. So that means, for example, with Boston Sight, you have selected an IG lens, diameter 18. It is telling you what is the best sagittal height, it's telling you the best base curve, and it's telling you for all 4 quadrants what is the best haptic. So it depends what lab you're working with, but both options are available. So to visualize it a little bit, so the base curve is, we try to align it as uniform as possible, and we're always looking for the optical zone of that specific lens. So it might be an optical zone of 8 millimeters, and in other cases 10 millimeters. So it's always typical for that lens design. SAC prediction, the same. It is looking for the point where the lens is landing on the eye, so the first point of touch. It's adding the settling plus apical clearance. It's giving you the sagittal height. Landing zone, as already mentioned, we're aiming for a near sealed fit in most of the cases. So it's trying to align the landing zone as good as possible with the shape, the tangent of the scleral zone in each quadrant, if that's an option within the fitting or within the scleral lens design. Easy. This is the screen which I've been showing already before. And all the data that you see here is what we believe is everything that you need when you're working with our measurements. So let's zoom in. First of all, the first lens fit prediction. We believe that these three maps are the most important when you're reviewing the data and before you start ordering your lens. So it's the visor elevation map, the tangent angles map, and the scleral profile. I'm not going to discuss them right now, but we have a lot of webinars already discussing them. On the bottom left, we may show buttons connecting you directly to the lab. This is going to be a new feature which I will discuss later on. We also have the manual way of designing a lens. I'm not discussing it right now, but we're showing it on the upper right corner. So if you want to work with chord lengths, feel free to use it. The over-refraction tool and the HVID. Well, the HVID is very important for the selection of the lens diameter. Quad specific. Well, quad specific is pretty new, so only since last year's LS, maybe the one before, labs were coming up with quad specific designs, and we show it this way. It used to be a little complex the way we've been showing our data. So with our latest update, we've been making it easier to understand. So we show it this way. The data is shown clockwise. So the first landing zone is always on top. So 12 o'clock. 2, so landing zone 2 is always on the right side, so it's at 3 o'clock. Number 3 is at 6 o'clock, and number 4 is at 9 o'clock. We're also showing the Tabo system, so 90 degrees, 0 degrees, 270, and 180. And beside of that, we're also showing these arrows pointing in the right direction, so hopefully nobody will be confused anymore. And here it's a summary again, lab by lab. So Boston site is using the 1, 2, 3, 4 steps, and Pausch and Lomp is using the Tabo system with the 90 degrees, 0 degrees, 270, and 180. At this moment, we have the next designs included in our algorithms. The Zen lens, the OneFit Boston site IG, and the XL Atlantis Quad. Beside of that, it's also possible to work with AccuLens, AVT, and Valley if you want to have quad-specific design, but then you have to contact their consultant and push out the measurement. Here I have one example. This is an eye from a colleague of mine, which I always used to test my lenses, because he's oblique, his sclera is oblique in shape, so you can see that here. So the red colors are indicating that the flat meridian is located superior or oblique, and the blue colors are indicating the steeper meridian. He has dry eyes, and for me it's always hard to fit, because the lens tends to to shift temporal inferior. Here I have once more the little video how the selection process works, selecting Excel, selecting the Atlantis quad, a 15mm lens in this case, hit calculate, and there is the prediction. So this was the lens that I've been using, a chamber sec of 3200, and the 3 scleral sacs, as the way they call it, flat 2, steep 4, flat 3, and a steep 2. Showing how it looks like. So this was just the first fit that we have done. I believe this is the perfect fit, so smooth looking edges, no impingement at all. So for me, the perfect fit. Centration, perfect. Usually lenses tend to shift on his eye to the temporal inferior position. With this quad specific lens, I have the perfect centration, and the clearance after 1 hour is perfect. The arrows indicating the front and the back of the lens, as well as the tear thickness. And the last, what I'm going to discuss is we're always trying to improve our algorithms. So for Eaglet Eye, it's very important that we keep improving our algorithms. So the next thing, what is coming up, are the direct connections to the lab. So our first release will contain a connection to the Boston Side Scleral website, so you can order your IG lenses straight away, just hitting calculate. The lens is calculated, and you hit the Boston Side Fit Connect button, and all the data is pushed into the Boston Side website. And there you can order it. Similar also for Blanchard, we will have the connection up and running within a few weeks. So similar process, you hit calculate, you hit the one fit button, and all the data is pushed in this Blanchard tool, where you can do fine tuning of the Blanchard specific values like M and L values. And last but not least, at this moment, we're also working on integrating our data in the ScanFit Pro, which is the scan system of the iScan Pro, of iPrint Pro, let's say it correctly. A lot of work to do because it's a complex lens, but we are already testing, and actually a few weeks ago, Kyriakos, based in Cyprus, has shown the first test results on Facebook, so you can all find it. That's the end of my part, so I will hand it over to Barry, so Dr. Leonard.
Hey there. Thank you, Renier. Good day to everyone. I say good morning from California, but I saw there's somebody from Australia and it's 1 in the morning, so wherever you are, hi. I've been using the Eaglet now for a few years. I always thought I was one of the first to have one here in North America, and it's just been a great tool. The case I want to show you now is really what happens pretty much every day using it. If it comes up here, the first one, this case is as I said, a 41-year-old woman who had post-LASIK ectasia. She said she had some kind of LASIK in another country. She was wearing some ultra health lenses, seeing about 20/60 and 20/40 in the other eye. Not real comfortable, not real happy. She did have pretty dry eyes, thyroid disease, was using Xiidra and some artificial tears. So the next slide will show the topography. We looked at, of course, the rest of the exam. She had clear corneas, no scarring, anything else, but certainly a unique topography, not a huge delta in the, sagittal, the corneal height. So we considered other things. You could even look at an RGP, maybe things, but it's, as we know, it's always hard to get those to perch on these unusual shaped corneas post LASIK. And with the dry eye and that, we said, let's move right into sclerals. And she had looked into that a little bit, and that's sort of also where the direction she wanted to go. So the next step was running her on the Eaglet, and these are some of the first looks at her eyes that we could see. And what's really good, I mean, Renier was talking about, my dog just walked in and took my microphone, is, we get these scans, and for me in the real world, what's just the first step is pulling that correct diagnostic lens out of my kit. So we look at the ESP data, and we get the HVID very accurately. I always thought I was pretty good using a ruler and saying that's the HVID, and I found, I guess because of parallax and things, very different than reality. So sometimes you're starting off with whatever diagnostic lens you could think of, and it was too flat, too steep, too whatever, and then you get 2 or 3 or 4 diagnostic lenses on their eye before you even started. Now, using the Eaglet, the first diagnostic lens, whatever kit you're going to use to get that over refraction, at least you get that first lens on. So this was her Eaglet measurements. We can see she's definitely also a little bit oblique in her scleral topography, and those arrows are pointing to some pinguiculas, which we're going to end up dealing with later. So in the next slide, I believe, see what you got, Renier's. Yeah, this is the first lens fit. So I decided in her case, we were going to go with the Zen lens. At the time, especially back then, I was doing a lot with their microvaults. I now with Boston, with their channels, it probably would have been a consideration also at this point, as well as notching other lenses and that. But we ran the first lens fit. We had the HVID. We knew we wanted a 16 millimeter lens, and then you can sort of see the data with the sagittal height, also the base curve and the APS. And what's interesting is it does give you that base curve, and most of the time you're going to find that sagittal height of that diagnostic lens is going to be pretty close to that same base curve, but not always. And that's where we can start to really use this data, as we can know the sagittal height, but we're sometimes going to start manipulating that base curve to get even a better alignment with the cornea. But generally, with the kits that are out there, everything seems to match up. So we went to our Zen lens kit and to go to pull out the first lenses. With this case, at the time, I had I have interns in my office, and this was someone who was doing their contact lens rotation. We discussed this. Her automatic refractor showed like -15 with 5 diopters of SIL. And so we started having the conversation, well, are we going to do more of a prolate or an oblate fit? Because that's still going to be up to us as a doctor. And I had the intern sort of do both, because I was trying to teach him a lesson, because the first thing he said, by looking at topography and other stuff, it's a weird looking cornea, but he pulled out a more of a prolate shape, and which is almost what it says there, about a 7.4 base curve. But the problem is then the lens, you had a big high minus over refraction. So we ended up going with a much flatter oblate shape, but using our sagittal depth, and we ended up with a 9.5 lens. And that way the lenses end up more like about a +1, so a nice thin lens and better optics. So the next slide, I think, let's see what Renier you've got. This is then the lens on the eye after we dispensed the lens. She came back for her first checkup. Now I like to fit about 200 micron generally clearance. Most of the algorithms are set for about 300 in the Zen lens, and I think in the Boston and others. So what this had predicted initially, a lens of, let's see, I'm looking at my notes, I think about 4800 on that right lens, and I ended up with a 4700, so it matched perfectly. And I think the left, it's got a 4750, and we did a 4650. So we're in that range of 100, 150 microns, because I'm usually adjusting that to my personal preference. But that first lens, and then we followed exactly what the APS says, that flat 5 by standard on the right and a flat 7 by standard on the left. And what was interesting for me when I first started using this technology, I would look at that, and I'd look at the eye, and I'd look at the diagnostic lens of the eye. I go, no way is, it would say flat 7 by steep 9, and I'd go, there's no way that can be right. And I'd start trimming it down and going back to my old school art of fitting these lenses. And ultimately, we'd end up making a change or two and be back right where Eaglet said. So I really learned to trust what it says. And this one we ordered straight out of the box. Again, I adjusted the sagittal height, that 100 microns for my liking, and fit exactly the APS, and it was a first lens success. That lens gave her 20/25 vision. She came back, and then if you go back to that OCT, you can see it was sort of a nice alignment with the cornea. And then if we go to the next slide, Renier, when she came back, for the first checkup, we found everything perfect, very happy, but she did have a very slight impingement on those temporal pinguiculas that she has. So this is now the Zen lens on the eye at a follow-up visit after we'd gone ahead and put the microvaults. But you can see the other slide was pointing to the hash marks. And what was interesting, if you look where that's aligned, and if you went back to the Eaglet, which we don't need to, but it has the, it'll predict the axis of the flat meridian, and it was almost exactly there. And it lines up. We looked where the pinguicula is on the Eaglet. It actually can measure those. And then if we do a Lars adjustment, so there it is, and there's a way with putting your scrolling over that with the arrow, you can measure the elevation of that pinguicula and the diameter and the location. And then by using Lars for the rotation of the lens, we can tell the lab exactly where to put it. And you can see those 3 little dots. If you're not familiar with the microvaults, they put those around so we can see it where it lands. And boy, it hit bam right on. And that little bit of impingement that she had, which was bothering her, was taken care of in both eyes. So we had, in this case, I mean, first lens success as far as sagittal height, APS, everything. I tend to wait down the road for putting in microvaults and other stuff. We can predict that lens rotation, but sometimes we can be 5, 10, 15 degrees off, and I think we can hit it much better on a second lens. And even the labs are going to tell you, hey, make that first lens, and let's add things if we need to later, maybe if there's a front toric, or the microvault where we know exactly that lens rotation. This is the other eye, again, hitting right on. She does show a little pinguicula in the nasal, but that didn't seem to have an issue with her. But you can also deal with those if you need to. I think that's it. I don't know if there's any questions about that, but that's the real life part of it. A much better product at the end, less follow-up appointments, so much better for me in my office, much better for the patient to get a better product with much less visits, so everybody's happy. Thank you.
Very, very well done. Very well done. Thank you very much. Renier, can you let me share my screen? Okay. Here we are. Okay. All right. Again, Barry, thank you. Thank you very much. I thought it was a very good dig into.
I see maybe before you go, I see there's a question from Karen Garcia at Boston, and the image acquisition. And over the years, with the dry eyes and anybody, it's getting a good image. The dry eye patients, we try to have them, like in that case, she came in, she was wearing some hybrids. Now, a hybrid lens is probably not affecting the sclera that much, but anybody who's got a lens, a large diameter lens, a hybrid or a scleral, we try to have them come back another day that they've been out of their lens. So we 24 to 48 hours if we can. Now, it's not easy. Like myself, I can't take my scleral lenses out for that long because I can't function, but there's ways to get around this. So we had her do that, not wear her hybrids, and we had her use a lot of artificial tears in that 24 to 48 hours before to get the eye nice and wet. And then we have, in getting the acquisition, we found that using Blink with fluorescein, and we get a really nice fluorescein coverage, and we get some really, really good images that way. And anybody, if you have questions on that, you can always contact me, and we go tell you exactly how we do it in the office. All right, Tom.
Barry, thank you. And on that note, I've got something going on in my head that's suggesting that Monica Shea has a question. Monica?
Oh, can you hear me okay?
Yeah.
All right. Yeah. Well, that really is a follow-up to the original question that Barry just answered. And I was wondering about, especially for dry eye patients, capturing that image, if you use a little bit of an eye drop, a lubricant drop of some sort, letting that dissipate for a few minutes, does it affect the accuracy of the measurements by adding a little bit of artificial tear to improve the quality of the fluorescein?
Well, that is what we use. We use artificial tears. We like the Blink gel for the measurements. We first put a drop of fluoresce in. It gets a nice coating, and then the numbing makes it easier to hold their eyes open. We find there's more comfortable, and then we use the Blink gel infused with fluorescein, and we get a really nice, good data from that. And that's over the years. We also do, and if it's real dry, we also sometimes paint the sclera with the strips. We take 2 strips, put a little more blink on there, and paint where we need to, and get our first 3 images on each eye. If we find there's areas that are still dry, then we're going to really have to be painting more. And we've got that down. Our techs really have that down to a science, and then getting that eye opened up as wide as we can. We're able to get out, 90% of the time we're getting these, 17, 18 millimeter or more measurements.
Yeah, if I can chip in there, Langis Michaud in Montreal has done some research into this, and he's shown that after a few blinks of the patient, after you apply this blink gel, it will have reduced to a thickness of 1 or 2 microns, and so will have no significant effect on measurement. If you were to turn to something really thick and gooey like a Celluvisc, for example, there you might expect some results. But of course, that is not for your average keratoconus cases. So there's been some research done in that, and they've found no effect.
Thank you.
Okay, next question. Somebody shoot. Go ahead.
Tom, I had a quick question about the images were excellent with that central vault. The sample was, I believe, was like 175 microns in that range. What about the accuracy of how these lenses are fitting the limbal zone? Do you know that first fit over the limbus? Is that also very accurate?
Barry, Renier?
Well, I find it is, and that's where in most of the cases the base curve and the sag all match up. But there are cases where especially that base curve prediction with the sagittal height really can help that limbal area. But I think in the algorithms, and Renier has that, I've learned now over the years to listen to him and to understand the technology, but you can just accept it and use it, which is even better. But it really does get that limbal zone locked in.
So thank you, Barry. So Ken Mallor, Ken, it's nice to meet you. And I got to ask, is that a virtual background or a real background? So Ken asks about the time it takes to acquire a good image for both eyes. I would say for both eyes, I would say my guess is 3 to 5 minutes per eye, depending on how much experience you've got or your techs have got. So let's say 8 to 10 for both eyes. Does that sound reasonable? Arnie, Renier, Barry?
Yeah, I think with, sitting the patient down, getting everybody ready, getting all the drops, you got 10 minutes.
Right.
That's about it. But and with two, and it does take two people. I mean, you got to have two techs or myself and a tech or something. So there is that. But that small investment of time, with making first lens fits, you sure that more than make up for that down the road. So
yeah, I'm glad you helped me clarify. I was talking about start to finish, having the patient sit in, get her lubed up, till the end. And Brooke mentions that the image itself, click, 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 is faster than the processing time. Now the processing time depends on how fast your Wi-Fi is or your Ethernet connection to the cloud. So the 500,000 data points have got to go up to the cloud. It's got to be processed and then back down. So that could be anywhere from 10 to 30 seconds, depending on your internet speed. Arnie, would you agree with that estimate? You're on mute.
Yeah, that's a fair assessment.
Okay. All right.
Yeah, it's about or around about the ballpark.
And Ken asks, is it ever processed locally? No. The reason
Tom. The measurement itself is processed locally.
Okay.
So that's indeed depending on your processor speed. It also takes 5 to 15 seconds because processing the 500,000 data points. And the first lens fit algorithm, that's done in the cloud. So none of the algorithms are running on the computer. So that's to clarify it.
And then Eric Schweitzer, hello Eric, nice to meet you, asked the question, any insight into why you would not have a good first fit? What are the common causes?
One of the common causes could be complex shapes, and therefore we try to, or we introduce the Scleral shape map to show if it's really irregular. So if you cannot get away with a quad-specific design or a toric design. So, for example, very large pingueculae or anything what's making it more irregular, very inferior located cones that might be problematic as well.
And I think now with the addition of the quad specific that I've found now with moving from obviously spherical haptics to toric haptics, and now majority with quads, I think you're going to get even better first lens fits because you're just making a much better customized lens.
Okay, all right. Yeah, so let me clarify. There's image acquisition. There's the processing to get the results that happen locally, and then when you do a first lens fit, now you're talking to the cloud, and so all those steps, you're dealing with 500,000 data points, so all those steps take a little bit of time. But I was trying to help people get on, and I might have missed this, but Renier, did you go through Scleral Profile?
No, today I did not discuss the Scleral Profile at all.
Can you quickly go through that as maybe a step before first lens fit?
Give me a moment to pull something.
Sure.
Tom, I can add in a little bit of comments on the processing time.
Sure, Brooke, go for it.
So what we have done is I've taught my tech the information that I like to get off of the scan. And so, we'll take the patient in, we'll do the topography, and then I'll take them back and do something that we would need anyway, like baseline refraction or something, because we're usually managing the keratoconus. So we'll do a baseline refraction or something else that typically I would do versus my tech. And so she will then make sure all the data points, and she'll often run, I like to know what the scans would look like if it was a toric or a quad APS or, whatever your, the landing curves. And so she writes them both down for me. And then I look at that. So she kind of, while the the data is processing, she gathers all the data for me and then brings it to me while I'm doing something with the patient that normally I would do, you know, evaluate the cornea or refraction, something like that. And that kind of helps with downtime so that you don't have to rush and, you know, settle for data that you maybe don't think is as good. You know, she'll run a couple different scans and process the data to see what looks the best, you know, those types of things. Helps us minimize slowdown. So that really doesn't, processing time, even though it is, to me, the slower part. And it has helped when we hardwired to the wall for the Wi-Fi versus doing Wi-Fi. So we have our ported. That has improved processing time for us too.
Right. Good tips, Brooke. Thank you. Thank you. Renier, I've stopped sharing so you can take over the screen.
So
You're on mute, Renier. You're on mute.
Sorry.
Okay.
Yeah, is it better now?
Yes.
Yeah, buying me some time to pull up the correct slides about the Scleral Profile. But I noticed that
We're seeing the image acquisition and we're seeing the alignment dots. And you're on mute again, Renier. Are you swearing at me in the background for making you do this?
better now? Am I?
Yeah.
Can you hear me
I
again?
can hear you fine.
Okay, great. Yeah, okay. Somehow the video stops again and again, but I would say the image acquisition itself, 3 images, is about 30 seconds. And you see this is not the perfect measurement because there are 2 eyelashes folded down, but still the process itself is rather fast. So the preparation time, that's where you have these 10 minutes coming from. Meanwhile,
and hold on a second. Give me a chance to jump in. So, and unlike another scleral topographer that will remain nameless, we recommend 3 images because the patient's there and they're ready to go. So snap, snap, snap. It's not like we're merging these together with different gazes. It's just because they're there and you can do it and you can pick the best image.
It's good practice with any measurement device. Never just rely on a single measurement. Always take more, and have a quick look if they are reasonably comparable. And if you see that they are, you know you can trust the data. It's just good practice with any measurement device, whatever you're using.
Is this focus automatically, or do you have to focus it yourself?
You have to focus it yourself, but we believe we've created a very intuitive system to help the operator do that.
Okay.
Can I go about the Scleral Profile Map? So this map we've introduced last year's LES, so last January. It's a simple system helping you, giving you a quick feeling what is the shape of the limbus and the shape of the sclera. And it's just trimming it down to 4 options. If it's more or less spheric in shape, toric, quad specific, or more than that, so more irregular. What does that mean? If it is spheric, it means that all 4 quadrants are having no bigger difference, so no larger sagittal height difference than 100 microns. If it is telling you it's toric, it means that the opposing quadrants are more or less the same, and that the difference between the opposite meridians is more than 100 microns. If it is telling you it's quad, it means that 1 or more quadrants are having more than 100 microns of difference. And if it is irregular, it's not following the rule of being quadrant in shape, most often it means that there is a local elevation. So for example, a pinguecula. So most often it's coming up with irregular when there is 1 or 2 pingueculae present. It is analyzing it ring by ring. So it means that you have information of the inner zone, the limbal zone, and also beyond. So it is what you see in the last image, the fourth image, you see that the limbal zone is actually spheric in shape, but if you go to the sclera, there is this pinguecula, you can see this white dot, and therefore the algorithm is coming up with this is irregular in shape. Any questions about Scleral Profile Map?
So in that case, you would use perhaps either a notch lens for that irregular example you're showing. So you could do maybe just a toric haptic with a notch.
Correct. Yeah.
So then you would be able to take this image and force it into the toric calculation?
Yes, indeed. You can do that. We urge you to be careful. As mentioned in the beginning, we try to reduce and remove pingueculae, but if it's really big, really large, it might be very hard to detect it. So it may come up with a false too flat prediction. So therefore, if you see these irregular rings, so these yellow rings, we always recommend you to be very careful and preferably share the data with or the Eaglet team or your lab, because most of the labs do have one or more people on board knowing the Eaglet system as well as having the software themselves, so they can load your image and check it as well. So therefore, yes, you can use the first lens fit algorithms, but be careful.
So you're saying be careful with pinguecula, that's causing an issue?
The pinguecula itself is elevated, so if the algorithm is picking it up, it will come up with a false prediction for giving the landing zone, making it too flat. So that may happen.
If it's large, if it's a large pinguecula.
Correct, yeah.
Okay.
Yeah.
All right. All right. Okay, Renier. So Tiffany would like to see the software and where exactly you bring up the Scleral Profile Map. Do you have software running?
No, so buy me a little time.
Sure. And while you're doing that, yes, Ken, the Scleral Profile Map is automated analysis done by the software. That's correct. So any new scans, there's a bunch of people on this call and this webinar that have obviously got an ESP. And Arnie can probably explain a little bit about what was going on there, but the Scleral Profile Map only applies to new scans. So, but it's automatic. Arnie.
Yeah, that's exactly right. So we were well in discussion with our users, we were trying to find ways how we can find a nice way to graphically show to everyone what the asymmetry of the eye is. And so this is the first kind of thing that came out of that dialogue with our users, and that we launched in the GSLS in January. And it is true that you need to have a new measurement, so anything with the new software that was launched in January in order to see the profile map of the eye. It cannot retrospectively do that.
So I have the Scleral Profile in the software itself. What was the question exactly, Tom?
I think Tiffany wanted to see where you bring it up, where you access it specifically.
Okay, yeah. So you can only see it in new measurements, and it is just a little below. So just, this is always the starting screen, the bisphere elevation map, and a few tabs lower is the Scleral Profile Map.
So you switched your color coding here because your bias.
Well, what we in fact have is
red
quite a
and
sophisticated asymmetry calculating algorithm. So it's you shouldn't see it as another kind of elevation map, because it's not. It's just a pattern recognition algorithm that will compare different zones, both concentrically, so from the center out to the periphery, as well as between quadrants. And so the colors is just to highlight to the user what the asymmetry of the scleral shape is.
So there's no connection between these colors and the colors on the elevation map.
That's correct.
Right,
yes.
right.
Yeah.
Okay.
Keep in mind anyway that colors are just colors. Whatever map you're pulling up, the colors mean something different.
Yeah, so always check the sidebar for what the colors actually mean for that particular map. That's very true.
Okay. All right. Any more questions before we wrap it up? It's pushing an hour, so I don't want to hold you guys too long, but we're here as long as you need.
Ken Meller asks about the resolution. Yeah, standard. The difference that we keep is 100 microns. So it's checking each quadrant. Is there more or less than 100 microns of difference compared to the other quadrants? You have the freedom to change it yourself. So in the settings, you can change this value here, and you can change it to 150 or 200 to your liking.
So that's not to be confused by the resolution of the image of the sclera itself, which is 10 microns. This is just, yeah, okay. All right. Any other questions?
So when I look at this image, so you don't necessarily have to hold the eyelids open. It's on an as needed basis, right?
No.
No, you need to hold the eyelids open.
You don't.
You do.
You do.
Yes, you do.
Oh, okay. Because this image, this is just like an overlay, or?
This is definitely not the best image ever taken. What you notice here is that the eyelashes were not firmly pushed to the orbital bone. So you should have done that actually. Yeah, correct.
Yeah, so we use finger cots and really get a good grip on those lashes and lids and pull them open as much as you can.
So it's always a two-person job.
Yes.
Okay.
Most of the time it is not for all of our users. We have some practices where the operator, basically you ask the patient to pull down the lower lid. Most people can do that. And then the operator will reach out over the device and hold up the upper eyelid.
Yeah, and then an easy eye that can be done, but
yeah.
I think two is usually going to give you the best results.
Absolutely, yeah.
So it also depends a little bit what lens do you want to design. If you're going for a small Blanchard lens below 15 millimeters, you can do it. Barry likes to work with Boston Side a lot. 18, 19 millimeter lenses, you definitely have to yank it open as wide as possible.
That's a good point. Interesting.
The last question I suggest, could speculum be used? No, because the measurement relies on the tear layer. So we need to have smooth, good quality tear layer. So we keep the patient blinking between each measurement. We recommend the 3 measurements, have the patient at least blink once in between each measurement. So therefore just have the second person opening the eyelids.
Okay.
Yeah.
Okay. Ellen asked a question. Could a speculum be used, a thin one?
Yeah,
Barry?
that was the...
Oh, okay.
That's
Sorry,
what I
I'm
said.
okay. All right. So Renier, looks like you gave me access to the screen sharing back.
Yeah.
Okay, so we're going to wrap it up. And again, jump in with any questions you might have. Can you guys see my screen? See the presentation?
Okay.
All right.
Mhm.
I don't know why it keeps starting over again, but it does. And let me just move some windows around. All right, so good questions. Now we're going to jump in now, and I'm going to go through just the key points of differentiation. Up to 20 millimeter scan of the eye surface is a point of differentiation, certainly versus oculus and you know, corneal topographers and that kind of thing. Single shot, you get all the data you need in a good image with a single shot. 500,000 data points going up, getting processed and going up in the cloud and all that crazy stuff. Accuracy of the unit is 2 microns in the cornea and 10 microns on the sclera. And that brings up a good point that Monica had, a good question Monica had earlier this morning, and that was, could the unit be used as a corneal topographer alone? Well, certainly the resolution is more than enough. The software in the Eaglet will manage and monitor your patients appropriately. So you know, I would consider it a really good corneal topographer. And then the key differentiation I believe you've seen today is lab neutrality, and that is we have upwards of almost approaching 20 lab partners worldwide, and we'll work with anybody that'll work with us. So even if those other guys came to us and said, hey, we want to do an algorithm for the latitude, we'd probably consider that, but I don't think it's going to happen. And in most of the labs, there's at least one ESP trained consultant at each lab. Certainly our big partners like Boston and Alden / B&L and Blanchard and, you know, the biggies. So that's good too. So when you have a question of the lab, you can share the image. You can send them the MSR file, and they can bring it up. They have the software installed on their end, and you guys can talk about it. They can make recommendations, anything you need. And we have 40 plus lens designs across a little over 17 labs now. So let me just take a quick run through of the labs and the designs. I'm not going to bore you with reading them all off, but you can see there's a pretty good list, and that's just half of it. There's the other half. And this list is growing. Every month or so, we add at least one design or one key feature of a design. Renier is a busy guy trying to keep up with these labs. And again, the more we learn about the sclera, the more we realize this complexity, the more the labs try to keep on the cutting edge with design features. And that's only going to keep going. So next steps, we typically go to most of the major specialty lens meetings. Now, these are not typical times. So several of these have been canceled or will be canceled in our guess. But in a normal year, we go to GSLS, Dottie Fidel's meeting, the International Congress of Scleral Contacts, Vision by Design. There's a fair amount of folks up there that are doing scleral lenses as well as CRT.
Ortho-K, yeah.
Ortho-K, yeah. The International Summit of Specialty Contact Lenses, that's actually Dottie's meeting. The International Congress is Tom Arnold's, and AAO, we typically don't attend AAO per se, but we set up shop as close to the exhibit hall as we can and demo the unit up there. So we can obviously and look forward to setting up any one-on-one online demos for anybody anywhere that wants to dig into this thing and get a personal online demo. We can send a quote. And you can always send an email to either me or Arnie worldwide. My focus is on North America, and Arnie's is on what I call the rest of the world. But you can send an email to anybody, and we'll share it. So I want to thank you guys for joining us, and we appreciate your time. The one last thing I will point out is if there's interest in one of these, this might be a good time to get it. Now, I understand financially, things might be difficult for most of you guys, but it's going to take us a couple weeks, 3 to 4 weeks in these times to manufacture and ship it to you. But the time that you can get used to it and get the experience under your belt is now, when you're not loaded up with patients. So Barry, do you have an opinion on whether this is a good time or a bad time to jump into this thing?
Well, it could be. I mean, we are definitely having more time to look at things. So you have to play with it now, because when you're busy, it's sometimes tough. The other point, someone was asking about the corneal topography. I love my topography. I have the OPD from Marco, but there's times, as we all know, when you cannot get a topo or any good kind of topo off those, but the Eaglet does get it every time. And so it's really a nice little bonus.
All right. Well, thanks, Barry, and thanks to everybody. Thanks, Renier. Appreciate your leading us down the deep path, and we'll see you guys shortly, I believe. Stay home, stay healthy.
Yes. Thanks,
Ciao.
guys.
Thank you all. Bye-bye.
Thank you all.
Bye.
Talk to you soon. Bye-bye.
Bye, guys.